Welcome, everybody. Welcome to the IEEE presentation series on nuclear energy. My name is Michael Lüken, and I am the chair of the IEEE Planet Positive 2030 initiative, the coach of the Future SUSTEC initiative, and various other volunteer and other committees in IEEE. One of my great pleasure has been and is continuing to be to work on this IEEE presentation series on nuclear energy. And it's today really a great pleasure to introduce Dr. Niet of Simon Fraser University, who is going to talk to us about planning the future energy systems and do we go nuclear. First, a few words about the series. It's actually organized to start with by the IEEE Vancouver section, as well as the Future Directions SUSTEC initiative, NPSS, which is the Nuclear and Plasma Sciences Society, and IEEE. The series presentations are really intended for a broad audience, not only the engineering community. So it's for the general community with an interest in energy alternatives, industries, and so on. We want to serve the needs of the profession and the public by increasing the awareness and understanding of nuclear technologies. And of course, we cannot be biased. We are not biased to reflect any interests or concerns of only some interest groups. It's important that we stay and always are unbiased or neutral. So one of our previous IEEE presidents, Saifur Rahman, stated a couple of years ago that ensuring that our response to climate change is substantially appropriate and properly engages IEEE, its members, and the larger technical professions. In other words, looking at what IEEE can contribute as a technology provider and on a neutral platform. And here are the various organizations that are supporting this nuclear energy presentation series. I mentioned all of them before. This is the list of presentations that had been planned so far. We are now on number 3. Today is April 9, planning the future energy systems. Do we go nuclear? And then we have a number to go forward in roughly 2-week intervals, all the way to the end of July. And I issue right now an invitation to all of our attendees. If you have ideas for other presenters, other topics, put them in the chat, and we will see how we can come up with a second series to follow this one with new input. We also have started a mailing list for people who are interested in nuclear energy, and a mailing list for people who are interested in the print presentation in particular. So here are the 2 QR codes and links. And I'd like to give a quite little introduction as well for the next talk. It's by Dr. Jing Jiang from Western University, and he's essentially giving an overview of the development of nuclear technology in Canada and how it has contributed to medical isotopes and electric clean power generation ultimately via the fleet of CANDU nuclear power plants. And that is going to happen on April 23. And with that, I'd like to ask Dr. Niet to take over, and I'll stop sharing and invite you to start with your presentation, Taco. Looking forward to it.
Great. So give it a second for the screen to show up. Hopefully it does show up there.
Perfect. It's there. Excellent.
Yeah, so thank you very much for the hosts for inviting me to this presentation. talk a little bit about what I do at SFU in the School of Sustainable Energy Engineering at my Delta E Plus research lab. And sort of the topic is, how do we plan for the future? Do we do nuclear? Do we like nuclear in our system? Yes or no? How does it work? And some of the modeling we're doing. Let me check, does my clicker work? No, I have to click in the right place. There we go, now my clicker works. So I'd like to start, first of all, with acknowledgement of who I am and positionality of where I am. And I guess I'll include a broader introduction of who I am and the work I do also throughout the presentation when I talk about my group. So just to position myself, I'm an immigrant. I was imported by my parents when I was 2. I was born in the Netherlands, raised on Blackfoot territory in Alberta, and I currently work on the unceded homelands of the Nahonam, Squamish, and Salish-speaking peoples. This is a picture of my the forest that I can walk to from outside of my place, and I just really appreciate the beauty of that space. And you can see my background is my sailboat, and I really appreciate being able to sail around the beautiful Sainath Quayam and Atlakatsum areas, so Indian Arm and Howe Sound here in the Vancouver area. It's a beautiful place. Part of my work and part of what I want to do is look for how we make the world. Apparently my scrolling isn't working. Make the world a better place for everyone involved, and that includes transitioning our remote communities off of fossil fuels, increasing air quality, and also working with countries that have less fortunate situations than we in Canada do. Especially in BC here, we have lots of hydropower. We have a really clean electricity system, but the challenge is, how do we move forward from that, and how do we decarbonize a lot of the different pieces? And it's not just the electricity system that we have to deal with. Nuclear is one piece that is mostly electricity system, but we're piecing a lot more of those pieces together. Hopefully some of my modeling will help make good decisions, which will help move us forward in reconciliation and addressing colonial harms. And that's what I hope is part of my work. So just a quick outline of the presentation. First, sort of 4 sections. Talk about the challenge. I think all of us here probably understand the challenge. If you're here, I suspect that you're actually part of understanding the challenge because you're interested in what that challenge looks like. But it's still valuable to sort of have a look at what the challenge is and why we have this challenge and where we're going with that. Then talk about my research group, an engineering research group at SFU, engineering approach, how we approach these challenges, and then some specific BC model results, which are actually hot off the press. My grad student, who I think might be an attendee right now, spent some stressful time yesterday running a bunch of different scenarios with nuclear in our modeling to show how things work. So the challenge, we know about these climate impacts in British Columbia. So in 2021, we had the Lytton fires, and then a little later, we had a large amount of flooding in BC here. There's been fires every year since in different places. There's lots of droughts and floods and things happening globally. Climate impacts are happening, and they're a challenge that we need to deal with. So climate impacts, how do we deal with those? How do we make sure? And it's actually a twofold question. One is, how do we reduce those impacts moving forward? And the second question then is, how do we mitigate the impacts going forward as well? So we want to reduce those impacts by reducing our emissions, and then how do we mitigate the impacts of these things? The Lytton fire, for example, shut down the train line and other pieces of infrastructure in that area. So it was quite impactful to those that community itself, just like in the Abbotsford, the floods, that community itself, but also the infrastructure connections. And when the Abbotsford floods happened, Vancouver was cut off from the rest of Canada by road and rail for a while. And that causes significant resilience challenges as well. Moving on to, so that's the climate challenge. So we want to move ourselves from energy that is fossil intensive, emissions intensive, and we want to make a resilient system. And the current situation, the numbers are slightly different depending on what jurisdiction you look at, but basically our current system is 20% electricity, 80% fossil. So that 80% fossil, so if we look at the electricity system right now, some of that's fossil as well, depending on where you are, but 80% of our energy is directly fossil with things like heating our homes with natural gas or oil, with transportation, all these different pieces. So industrial, commercial, residential, heating and things, transportation, all make up this 80%. And so what we need to look at is how do we address that 80% and how do we make that 20% as low carbon as possible? And so BC, we're in really good shape. We have lots of hydro. So the 20% electricity in BC is low carbon. But addressing the 80% fossil, we need to move that 80% fossil. A large part of that will be transportation electrification, heating electrification. The more we move to electricity, the general consensus is that moving to electricity is going to reduce the amount of fossil energy we need. And there's two reasons for that. One, we can have low carbon electricity. And the second piece is that we can be more efficient with non-fossil energy. So engineering people, we can do math. So the 80% fossil, that's 4 times what we currently do with electricity. So the idea would, so the 20%, we multiply that by another 4. We need 4 more electrical systems to decarbonize that 80%, electrify that 80%. However, efficiency means that it's really only 2-ish, maybe 3-ish full electrical systems that we need to build to make, and they all have to be low carbon to make that all fit together. And so that's a big challenge. How do we deal with that 80%? So just looking at BC, BC currently has about 50 terawatt hours of electricity per year. Most of that is in hydro generation. Site C adds 5-ish terawatt hours. We still need another 20 or 30 Site C dams to be able to scale up to the two times the electrical system. And just to give us a sense of scale, CanWea says that we can do 55 gigawatts of wind in Canada, which would be about 168 terawatt hours total. But we'd need to do all of that in BC to meet the demand, and intermittency is a challenge. How do we deal with that storage and those challenges? And then there's other options, efficiency measures, so we need less system. We absolutely need those. Nuclear, maybe SMRs, that's part of the discussion in this discussion series. And other options, what other possibilities are out there? Do we want to do biomass? Do we want to do biomass with carbon capture and storage? How do we piece those pieces together? And that's really what my research group is about, is how do we piece all of these pieces together? So, and I want to put this in the broader challenge as well. So we know we want to decarbonize our electricity system, and we want to move as much of our other energy to electricity. And we want to do that without damaging sustainability in the broader sense. And so the Sustainable Development Goals, no poverty, hunger, education, equality, we want to address all these in a consistent manner. And so part of the modeling that my team does is looking at how do we electrify, how do we build out this system, but then look at the implications on some of these other pieces. That's other work that our group does, so I won't spend a lot of time on that in this. Most of this will be the technical sort of system expansion discussion, but these other sustainability, these other goals are really an important piece as well in terms of what we want to address going forward. And one of the challenges with that is that these are all interacting strongly. So there was an interesting study for the International Council for Science, which looked at how these different pieces interact. And so you have the affordable and clean energy here, and it strongly interacts with hunger and good health and life below water, and then interacts in other ways with all the other SDGs as well. So there's this really interesting linkages and interactions. And so the challenge is multidimensional, multifold. I'm trying in my research group to address multiple pieces of this, and working with other researchers at SFU as well to address multiple pieces of this. And then, as I said, this specific discussion will be focusing on that electricity for BC piece and looking at that specific question in a little more detail. So that's sort of the challenge, intersectional, global, big picture challenge. And then my research group looking at how we address that challenge. And so my research group is called Delta E+. So delta is change. So engineering symbol for change is delta. So change is happening. We need to address that. E is for energy. So energy and all that entails. And then the plus is the fact that energy is connected to everything else we do. So it's not just electricity, we don't really care about electricity. We care about having a comfortable home. We care about getting between different places. We care about those different aspects of things and so it's really all of the other things that everything links into. How do we support good decision making? How do we make modeling tools that are fit for purpose? How do we model the linkages between land, energy, and water and food? And sort of data-driven open source modeling for transparent analysis. There we go. I'd be remiss if I didn't acknowledge that it isn't me that does most of this work. I did some of this work as I was doing my PhD and then into my starting of my career, but now I get to supervise a whole pile of people who do this awesome work. And so you can see my picture and Andy up at the top. We sort of lead this motley crew of wonderful people. And the wonderful work that's done here, Jocelyn and Elias, I asked them for some runs of the modeling, and they came through and figured that out in the last, even, I think there was some model runs still happening at like 8 p.m. last night to try to get the last little pieces in. And so really appreciate that I stand here because of all the people that I have with me and the wonderful work that they do. And so wanting to acknowledge their activities and their work. I get to stand here and take credit for it, but it's really, they do all the really hard work in putting all the pieces together. And so some questions I might actually have to refer to, say, I'll get back to you later, and we'll talk to the model developer or the modeler putting things together. I also wanted to mention that I'm a researcher in sustainable energy engineering at Simon Fraser University. I do energy system modeling, big picture, looking at countries, provinces, doing work in international development in different countries as well. I was actually just recently in Guyana doing some climate, land, energy, water system modeling there, helping their team at the University of Guyana build their own modeling group and sort of do some decision support for that modeling group in the University of Guyana. But I'm only one researcher at SFU in sustainable energy engineering. And then outside of sustainable energy engineering, there's a whole bunch of people also very interested in, I know people in planning and political science that are doing really interesting pieces as well. But I thought I'd highlight some of my colleagues at Simon Fraser University in the sustainable energy engineering research. We have research in water, thermodynamics, both for refining methane, but also alternate vehicles for fuels, optoelectronics and materials for carbon capture and interfaces for how that works, and solar panels. We have people researching trains and how trains interact with tracks and how that becomes more sustainable, air pollution transport, power electronics and grid. So my research is generally transmission level grid, not distribution level, though I do have some work in the distribution level. And then we have some people who are looking at power distribution, both in terms of what algorithms do we need for protecting the grid when we put a lot of renewables in the grid, and then also what are the power electronic devices that we put in there. A couple of people not on this slide are doing storage research, so that's Dr. Tina Shoa, and then and then we have someone doing building systems as well, looking at how we make more sustainable building systems. So lots of different people with different expertise. Happy to connect you with people if any of this interests you or you have interesting work in the area. I'm happy to make connections. There's only one taco at SFU, so you should be able to find me and send me an email. So now let's look at the engineering approach to how we make decisions and how our team and our group really looks at things. And that starts with, what is a model? Why do we have models? What do we do with things? And so models are tools to make decisions, and they model a potential, quote, real, end quote, world situation. So Civilization Game, which you see here, it tries to model a, quote, real world potential situation where you're trying to develop a civilization. And then if you do a policy of, at certain points, if you don't have a fire brigade, things burn down and that's bad for your civilization, or at certain points you might have an invasion from a different city, and these sorts of things are models of how the world might work. And engineering, we're trying to make models. That's really what engineering is trying to figure out how do we build something that is going to represent the real world. And that's what a model is. It's just a representation of that world. And then specifically for energy decision making, there's sort of a number of different types of models, and I sort of broadly three categories. One is the energy economy models, really big picture. If we put in a carbon tax, what does the economy do? How does the economy shift from high carbon technologies to lower carbon technologies? Often without understanding what those technologies are, because these models are such big picture, they have these equilibriums that they have to do, so they can't really represent individual technologies in any specific way. On the other end of the spectrum is power system models, where we're looking at the electrical system usually and looking at the specific, what's happening at specific times, what happens when we have a fault. So we have the power system, someone drops a branch on a line, how does the system react to that? And these are often sort of minutes type scale models where we run the system for a minute and at a couple of seconds in, we have this fault, and what happens in the fallout of that. Mariana Resner does a lot of that power systems modeling and sort of looking at how do we protect the system, how do we deal with renewables in our houses and everything. And then in the middle is this sort of capacity expansion type model. And that capacity expansion modeling is really where I do most of my work. I'm looking at how do we effectively address the demands we have and how do we build out a system to effectively do that. Very technology specific, so we're going to put nuclear and wind energy and what are the wind regimes and everything like that in our model, but we don't get down to the power system. So when the wind blows or doesn't, what actually happens on the electrons, we don't get down to that system, but we're looking at the energy flows in detail in that system. One of the things I just want to say to start with is all models are wrong, be that the model in your head of how we should build out nuclear or not, all the way to the most detailed model of a device. They're all wrong, but the question is how useful are those models? So we know about the UK CO2 emissions in buildings. There was a nice model for how we do that. So we made a building envelope rule. There was in or out air quality issues because of the change in emissivity or in airflow through the building, higher fuel prices, summertime overheating, leaky condo issues. So all these different things happened because we had a model of a building that we said, we're going to put this around the building, and that caused some issues. So one of the pieces of that, to me, is really important, is to address interdisciplinary teams, working with statisticians, behavioral scientists, policymakers, complexity scientists, so trying to link to a lot of different pieces. So my models aren't going to solve the problem. They're going to provide one piece of the discussion in solving the problem. And I think that's a really important piece to realize, is that no one person will tell us the answer. And I really like that we have this series of discussions so that we have a series of discussions about these different technologies with different perspectives to see how and what models are wrong, where are the models wrong, where are the models making sensible things, and what should we do as a society rather than just an individual discussion. And then the other engineering approach is conditional optimism. So there's a lot of examples of techno-optimism. Oh, we're going to solve the problem because we're going to solve SMRs and they're just going to magically solve the problem, this silver bullet. Or technological skepticism. There's no way we're going to possibly be able to solve this. We might as well go home. And so there's this concept of conditional optimism, which things get better, but they get better because we work at it. We can't just sit back. We have to actively work to make things better, but we can be optimistic that we can do it. Society has shown generally that we're very good at addressing these challenges as they come up. Yeah, so that sort of engineering approach, we model things, we know they're wrong, but we have this conditional optimism that as engineers, we can make things better if we work hard at it. Now my clicker isn't working again. Come on. Okay, we'll just click. So just quickly back to my research group and some of the modeling that we do. So one of the pieces is we do integrated analysis with a tool called PIPSA. So PIPSA is Python for Power Systems Analysis. And so we're looking at sort of how does the network, in this case, we have a US model, we also have a BC model, we have some modeling of different places in PIPSA. And PIPSA is a model that allows us to look at sort of the grid activities over hours to weeks to sort of a year. We can do a little bit of capacity expansion with PIPSA as well, but we're looking at how the different pieces connect, and specifically in some of this work, we're looking at how transport, electricity, heating and cooling, and the gas networks and the different networks intersect. And so we're doing that PIPSA analysis of how do the different models intersect, and we're actually looking at some trade as well in that model. Second type of modeling that my group does is climate, land, energy, and water systems modeling. We have a BC model where we'll show you some results from the BC model. We have a Canada model, but we also have a global model, and we're looking at how we can do this globally. So in Guyana, which I talked about earlier, we're looking at this climate, land, energy, water systems modeling. How do we address the land impacts of energy? How do we address the energy needs of land use? How do we address water and land water energy interactions? And this can be, we want to make sure that we have food security or other such pieces. So we're looking at how do these different systems interact, and there's strong interactions between these systems. And so providing a tool to say, okay, we want to import more food or import less food so we're more food secure. Well, what does that mean for our land system? We want to grow biofuels. What does that mean for our land system? How much land do we need? How much water do we need to be able to do that biofuel growing? And then also looking at grid modernization. The current grid is very, basically the transmission grid is not dumb, but the distribution grid is very dumb at this point. It was built a long time ago. So right now the transmission grid, you have some ability to communicate around the transmission grid, but once you get into the distribution system, it's basically you've got a substation and then it goes out into the houses, and there's no smartness there. If we want to add things like solar panels on roofs, we need to have some way of the system understanding what's happening in those different pieces. And so grid modernization, we're looking at a little bit about how the grids can be adjusted, or what things we can do in specific grid pieces to make that grid more resilient, to address some of the challenges, and then also protection. So if you have a bunch of distributed energy, you don't want to, one, cause issues if you have a fault, and then secondly, you don't want to hurt people if they're going to try and fix this fault. You don't want the electricity from the distributed energy coming back and then having live wires when you think you've shut down the substation. So some of those smart grid pieces need to be in there as well. Yeah, and so now I'm going to jump into our BC model and really explain what our BC model does and how it works, and then we'll look at some BC modeling results. So our BC model has sort of three pieces. It has an energy capacity expansion model built in osmosis, which actually includes land, climate, land, energy, and water. I'm not going to talk about the land, energy, water results pieces, but they are in there. We then have a link to a model linking tool, which takes the broad land or broad energy expansion for BC that we get from our capacity expansion model and disaggregates that into the different pieces. Because we need to know where, for our operational model, we need to know where these different pieces are happening. So, and then we have our power systems model, which is looking at how does the operation system actually happen. So we have these three different pieces. Their capacity expansion model, linking the results into our operational power system model. Next slide, come on. And so, yeah, so it's sort of a workflow. We have a raw data pool which builds scenarios into input processing for both our capacity expansion model and our power system model. We have this bidirectional linking, so we can run our capacity expansion and then run things through our PIPSA model to see how it works. And then we can feed some of that back into the capacity expansion model results to sort of get some optimal global solutions. Currently, we're running the capacity expansion and then linking that down into our PIPSA model. The feedback is still we can do that, but we haven't done that for the results I'm presenting in this piece here. And so we're looking for, what is this optimal solution? How do we put things together in a very useful place? How do we build these pieces and structure things in how do we make good decisions with that? So, and one of the pieces with this linking tool is this disaggregation. How do we get data for where and how we put these different renewables? And so there's land availability. We have lots of different layers. So we get a BC global, we want this technology in the model, and then we have to sort of break that down and say, okay, where is that technology going to be built? And so for wind, there's some wind up in the north here, there's some wind on the island, and land availability gives us what land is available in which areas, and how do we put that together? And so we need to decide where in the province we might build these actual wind plants, or where do we put these nuclear power plants? That's one of the questions we'll look at as well in some of the results. And then we have to build all the different pieces in there. So for hydroelectric, we need to have the time series of water inflows so that we can actually model the runoff and how it gets accumulated. And then also when is it available for running the hydroelectric dams? And so we get this series where there's some rain throughout the year, but really it's through the freshet. As the thaw happens up in the mountains, that's when most of the water runs into the reservoirs that we have in the province. So modeling of that hydroelectric reservoirs, and when does the water become available, and how much storage is in there to be able to address things like wind variability. Wind, we do a similar thing. We look at wind and we say, okay, what cells are available for wind? How are we able to put things together? What is the wind speed in these different pieces? What would a farm at that location actually be able to generate? And then what are the hub heights and CanWind and the Global Wind Atlas to sort of decide how our wind resource in the province works. And then once we've got our capacity expansion model might say we need 5 gigawatts of wind, and then the wind time series data, we process that to say, okay, well, that wind should be in these locations, and that's what we run through our PIPESA model for the operational pieces. Similar thing for solar. I don't have a slide on solar, but similar process of how that all works. And then the concept of how we address this modeling is we start with a general policy or some set of policies, which then gives us a scenario. What variables do we want to play with? We have some model inputs, results, interpretation, and then that hopefully gets us to policy recommendations. A lot of these pieces are not an engineering question, but a policy question. So it's not only engineering, but we're also looking at policy questions. And that's also where we want to interface to policymakers and colleagues like that to connect to those different aspects of the question, because it's not only an engineering challenge, it's an engineering policy, structural challenge, societal challenge of how we address these pieces. And then scenario formulation. So now we're going to go through this for our nuclear question. So in this question, the policies that we looked at was, do we allow nuclear in BC? Do we subsidize nuclear power? Do we restrict nuclear build-out locations for earthquakes and things like that? And so those policy questions, those potential policies, get us into a number of scenarios. One of the scenarios is, when do we allow nuclear to start? Will it build fast or not? Could we get it in 2028 or 2030 or 2035? When would nuclear actually come into the system? Second piece is cost of nuclear. There's NREL puts out a technology baseline, which gives us sort of base costs for different technologies. And a lot of people would say that nuclear doesn't ever meet that cost criteria. And so for this scenario specifically, we did, can we cost nuclear at the baseline value? What happens if it's double that, or what happens if it's 4 times that? And then the other variable we played with in our PIPESA model was, where do we put that power plant? So if we install nuclear, do we install it up in the Peace region? Do we install it near Vancouver, or different places where we can put that? And so that gives us those scenarios that we want to play with. And this gets us to actually running our model and doing the results. So this slide hides all the model running that we do, all the stresses with debugging things and all the work that Elias did. There's a lot of work in behind this slide, but here we're going to get into some of the modeling results. And so starting with, nuclear comes in even at a premium. And so what we can see here in this gray here is nuclear is built. In the base case, there's no nuclear allowed. And then in the cheapest version, we build a lot of nuclear. In the slightly more expensive version, we build less. And then the more expensive version, again, we build less nuclear. So we're building less and less as it comes more expensive, but we're still installing it and we're still wanting to use it. The model is showing that nuclear, so low carbon baseload type power, is really valuable to the system. And so that's an interesting insight, that it may be a value to the system to have this baseload power. So looking at the operation, so this happens to be the generation in 2040 for the standard priced nuclear, and we're allowed to install it in 2028, but this is a 2040 result. And so we run the power system in 2040 and look at what does it look like. And so we see this pink, in this case nuclear, runs basically constant throughout the year. And our hydro dam, this blue here, is really used to firm up the renewables and turn the renewables on and off, basically address the renewables variability while the baseline nuclear runs flat. One other thing you may, so that's sort of how nuclear works in the system. It basically runs flat and allows hydro to be available a little bit more to do that, that arbitrage with renewables. And so putting that all together into the three different, so there's the base where hydro has to do quite a bit more work than in the nuclear versions. Hydro is a little bit smaller, and basically the nuclear there runs baseload and allows us to keep some of the water and that flexibility in our hydro dams and gives us valuable flexibility in the system. So it serves the nuclear would, if it's providing baseload, really serve the grid reliably and allow things to work really well in terms of how the operation of the system goes. However, there's something really interesting that comes out, and that is that the reactors run really well and do really well for where they're installed, but the grid remains constrained. And so you can see here, this is the grid. We have a 28 region model, and we have the grid in between things. And with no nuclear, there's a number of different grids. So the red grid tie lines are heavily loaded, and basically we get almost exactly the same pattern if we have no nuclear, or we put some nuclear in the piece. If we up here, a bit more stable than down in terms of earthquakes down in Vancouver, but basically putting nuclear up in the piece doesn't reduce any of the grid tie lines. Those different tie lines are challenging no matter which system we want. So there's going to be some grid expansion needed no matter which technology we're using. And then the other piece is the grid congestion. So I actually see a question in the chat. I'm going to answer it right now. So what is backstop? In our PIPESA model, in our operational model, if there's a grid that doesn't allow enough energy to be moved in it, then the backstop is an expensive technology that we have to use to allow the model to run to identify these unserved hours. And so if we put nuclear in the piece, what we find is we have Squamish and the Sun, it's mostly Squamish, the Cowichan Valley and Victoria end up not getting quite enough electricity. So we have to have some load shedding that's happening there. Couple of megawatts is sort of the scale is quite high on here. If we move that same generation of nuclear power into the greater Vancouver area, then what we end up having is much less curtailment happening, and most of that ends up happening in the Victoria region. And so the location of this energy is really important as well. Not just do we need this energy in the province, but also the location of it. Where is it actually generating? Where are the different pieces, and how do we build out the system to address those different challenges? And then, so finally, sort of conclusions. Nuclear can benefit the system by providing reliable baseload power. It frees up hydro generation for grid firming with the renewables that we're going to need in the system. There's higher costs of nuclear that reduce the installed capacity, so there is a cost challenge there. Will we meet the cost projections of nuclear, and what is the appropriate sort of amount that we're put in there? Grid congestion in BC will need to be addressed. It doesn't matter if you have nuclear or not in the system, But where you put it is really important to the system, but also important in terms of safety. Would we put a nuclear power plant in the Lower Mainland, where we have a large population center, and also where we have potential for earthquakes? Or would it make more sense to put it up in the Peace and build the transmission line for that and the cost of that transmission line in terms of the system building? And it's a complex question. Nuclear has benefits and challenges. And I guess the final piece, building these models provides one tool to address some of these grid decarbonization challenges and how we address those pieces. I've given you some really quick examples, and not all the different pieces are in there. Like, for example, the amount of electric vehicle uptake we didn't play with that variable and how much different energy we'll need. But those are also different. All those different scenarios are ones we can play with in the modeling. So I will leave it at that, and then we have some time for question and answer, I believe, because I think, and I see some questions coming up in the chat and the Q&A, I think. So I'll let Micah take up the.
Thank you very much, Taco. That was a very, very interesting talk. I don't think I've ever seen an interesting talk like this about modeling. I will actually start off with one question. Like, of course, you are essentially using your models for ultimately building decision making, right? So how do models, forecasting, and digital twins come together?
Interesting question. So modeling and forecasting, I think, are two aspects of the same piece. So to be able to model into the future, we need to have some forecast of energy in the future. And that, I think, is a big piece of the question, is how do we effectively forecast what's going to happen given the political challenges in the world right now? How do we even effectively forecast what's happening next month, let alone 10 years, 15 years down the line? And I think there's tools in the modeling to be able to look at that. So do we do a bunch of scenarios at different levels and look at what's robust in the decision making? There's a number of tools under the sort of broad category of decision making under deep uncertainty. How do we make decisions into the future? And part of that is also like, how do we decide? Or part of that is if we run all these scenarios into the future, and in 2040 every single scenario says we're going to install 5 gigawatts of wind, we can be pretty sure that we can install 5 gigawatts of wind in the future. If the model has a lot of variability, now then we have to look at how do we increase that specific forecast to see what's causing that issue. Can we do some work to increase that accuracy, that forecast, or understand what is driving that so we can make good decisions based on that? And then you asked about digital twins. So digital twins are maybe a little bit outside of scope, but it's an interesting question. So digital twins allow you to basically take a system and create a model that allows you to see what that system might be doing and then have it input with actual current. So the example of digital twin that I'm aware of is jet engines. Most jet engines have a bunch of different sensors on them, and they have a digital twin sitting somewhere, and then those sensors come in, and the health of that engine is sort of constantly run through this digital twin to see if it's running well and does it need maintenance and things like that. There might be some opportunity to do some digital twins and some sort of machine learning algorithms for some of these pieces. And we do have some of that research going on in our lab, but it doesn't necessarily directly correspond to the modeling that we're doing or that I presented here.
Well, thank you very much. So I'm going to go and pick up the questions here. One is the last one, actually. So I'm going from back to front.
Okay.
Can we use nuclear beyond baseload and use it to follow load?
That's a really interesting question, and I think that follow load is also a very interesting question. So there's two sort of pieces that are in there. One, following load with nuclear has been done. France, for example, has quite a lot of nuclear in their system, and following a load, which load doesn't change that quickly. So following load is not necessarily that big of a challenge. The challenge is how do you deal with solar and more specific and more even more challenging is wind, where the variability can be quite drastic. So nuclear tends to be heavy thermal inertia, and so it's not as well suited for following fast changes in the system. BC is a really interesting place because, yeah, we have hydro with the flexibility. It's actually the previous question is that BC has abundant hydro that can provide flexibility to manage solar and wind. And that, yeah, that flexibility in the hydro system is really valuable. The model also likes that base load to keep that flexibility of that hydro so that we can do more of that wind arbitrage. And so it becomes a question of how much do you need to follow with the nuclear system and how much is the capability of doing so. And it becomes more of that's a technical engineering question of the nuclear technology, not necessarily how the system uses it, but following loads, following loads is generally, my understanding is generally doable. Following wind and solar variability requires some technical advances. Adding some battery storage or something like that could potentially provide some of that as well. So again, it is a system. You can't say, well, nuclear has to do everything, but nuclear with batteries, with wind, with hydro, how does that system work, putting everything together?
Yeah, the other piece presumably that also comes into it is demand side management.
Absolutely, yeah. That's demand side management, both for the total amount of energy that we need. So can we manage some of that energy so we don't need some of it? So then we have to build less. And then also, can we shift some of that demand to different times? So both demand shifting and then demand like efficiency and trying to reduce the demand itself. Absolutely.
Yeah, so I was looking at the previous comment there as well, but I don't, it's really more a comment that on the situation in BC regarding nuclear will only be practical if you're not able to develop practical long duration energy storage. So that's a comment on the financial situation, etc.
And I think it's also, we currently have hydro for a large part of BC, but if we expand the system significantly, then the percentage of hydro in BC is going to get smaller by side of the system, unless we build more dams, but that seems very unpopular as well. So,
well, there's also, of course, into the future, the issue of less availability of water in the hydro system, presumably, right? So there's a long-term forecasts in this particular case of circumstances that influence the system as well.
Yeah, and it's interestingly the climate predictions are not generally saying we're going to have less water, but it's going to arrive much faster in. So we saw the hydro was sort of a sharp it was had a few months in the middle. The expectation is instead of having a few months, it's going to come in like 1 month. We're going to get a lot more water and very quick, and then have to deal with that in the system. Yeah.
Well, the other question was respect to what assumptions you are actually applying to prevent you from using nodal power flow. So this is the modeling capacity expansion zonally, where you introduce challenges that, look at the linking of the different power system models.
Yeah, one of the challenges is that, so doing the power flow for a system, so if we have 28 nodes, we're trying to do that hourly for multiple years. Computationally, that becomes very heavy. And so we don't do the transmission or capacity expansion, and then we do that linking step because of the computational speed. So we can do very fast iterations, and then once we have sort of and you're absolutely right, we can do more of this solving the transmission, capacity expansion, hourly, all those pieces together. We can definitely do that, and then it becomes a computational challenge. And so we chose to do it this way to make the model relatively fast to iterate on. So we can run a number of scenarios very quickly, And then if we see this is what we should do, yeah, we might go into a more detailed power system model with those pieces, but that might take hours or days to run on the computer systems rather than sort of few minutes that we're trying to get to. So it is big. There's always a balancing of how detailed do you make your model versus how your computational challenges that you get with that as well.
Yeah, I can understand that. I used to do astrophysics, so
Right.
and handling the data and
Yeah,
the computations
for
was
sure.
one of the biggest challenges.
Yeah.
Let's go to the chat. And so the last question there is, I guess there's two questions linking together, whether you're considering only a conventional nuclear, like or Moltex, Natrium, etc., designs that have energy storage specifically focused on smoothing renewables, and then the linking with that, the next question, the availability of SMR or deploying SMR technology.
Right, yeah. So at this point, we've looked at conventional nuclear.
Okay.
SMR is just a smaller version of conventional nuclear usually. Maybe it's a little more reactive. We haven't looked at the specific energy storage on smoothing renewables in the nuclear technology itself. We do have storage. I do notice another question on storage and chronology. We do have storage in our model, and we do look at the chronology of storage in the model. That could be a whole nother seminar on how we do chronology and storage in the model. We've got a paper that we're putting together on how we do that. So that storage piece specifically, especially with big hydro, is important. How do we store that water, and when does it flow out? When does it flow in? And then we haven't looked at specific designs that have energy storage in them in terms of how they can smooth renewables. The model itself doesn't have the details of the nuclear technology other than is it available, the sort of rough operational constraints, and then we can change that and adjust for different reactors. But at this point, we've been mostly looking at sort of big picture, does that come into the system and how does it work in the system? And then we can look at, so because it operates in this way, maybe we should look at this specific design, but we haven't gone into that detail in the modeling yet.
Okay, so I guess one of the questions is the data piece. Like on the one hand, where do you get your data? On the other hand, do you generate data and where would it be stored?
Yeah, so data is always a challenge in modeling. We have there's BC Hydro provides some data on how loads work in BC. Then there's projections of so I talked about EVs earlier. What do EVs do to the grid demand? We do our best to make good, sensible predictions of that. So one example is with EVs, we have there's a number of different tools that are out there. NREL has some with typical EV charging profiles, and then we look at, so those charging profiles, what are the quantity of EVs in the system, and then we try and forecast, well, what if right now we have 10% EVs, in 2030 maybe we have 30% or 40% or 50%, we might have some variability there, and then we use those profiles to build our longer term projections. And then again, it's this sensitivity and scenario analysis of, does that change the system? Is it marginal changes, or is it significant shifts in how the whole system operates? And then we can look at, if it's a marginal change, if we have 30% EVs and the system works like this, and we have 50% EVs and the system works almost exactly the same, but it just has slightly higher capacity, then it becomes a timing of capacity question rather than a total capacity question, versus the other option where if we go from 30% EVs to 50% EVs and the system changes entirely, now that's a bigger question of how we deal with those pieces.
Yeah, so another question that I was thinking of was, like, you showed us your predictions, or your modeling forward to 2040 for BC. So what does it look like? Like, can you comment on another region? Like, I don't know, you talked about another country maybe?
Yeah. Yeah, I think the very different, yeah, so different contexts, different challenges. So in BC, we have a lot of hydro. In Guyana, they've currently found a whole pile of oil. And so they're looking at how do they're building a natural gas power plant to power their country. They've got very different demographics of population as well. They're having a massive population boom. They're dealing with land restrictions because they want to keep their forests because they have a lot of forest cover. We have similar things with forests here, but some of those pieces sort of how do we, yeah, so it's very different jurisdictions. So you need to sort of look at the specific, and I think that's partially not a modeling question. Partly it's a question of working with the people in that jurisdiction of what are the questions you want to ask, building a model that can address those questions, and then providing policy support with that. So it's, and in Guyana, they didn't have any questions specifically about nuclear. They're building a big natural gas power plant that should power their country for the next, that should give them enough power for the next 10 years or so. And then what comes after that, they haven't sort of looked at yet. But yeah, nuclear is definitely a piece there, and looking at what that looks like, how that's a question that they need to answer. We can help them build the model tools to make that question, to answer that question if that's a question they want to answer.
When you first started, you talked about the fact that you include land use and water,
Mm-hmm.
etc., in your model. So one of the questions here is when you're looking at the siting of nuclear resources, do you take the required water into account? Because your
Yeah.
last piece where you looked at the grid connections and the different siting.
Mm-hmm. That's a really good question, and I'm not sure I know the direct answer to that. I know that we can. I don't know if we've currently implemented that water piece for the power plants in the clues model. I know we can, and then we have to look at how the regionality of the land is put together in that model to do that. I'd have to ask Elias if we've done that piece of work yet or not. It's definitely an important piece. How much water do we need to run those nuclear resources? Is it available? If we put it in the piece, could we put it just below the dam and then the dam can run the water into there? How do those different pieces fit together? So absolutely, really interesting question.
So it looks like there may be some other questions in the Q&A I missed. So
Okay.
Ipsita, can you comment if I'm not seeing the same? Can you or Catherine?
Yeah, I'm just looking through the Q&A and
There was a question regarding nuclear with respect to how do you model chronology in your capacity expansion?
yeah, so so capacity expand the way we do chronology, we actually so there's a couple of pieces to that. First of all, we do some clustering of days that are very similar. So we say, okay, these 3 days in January look almost exactly the same. So we're going to cluster those together into one daily profile. And we do that for the year. We choose a set of days that are typically, can typically demonstrate the sort of general structure of the wind and the solar and the load data. And then the second piece of that is we actually chronologically stitch together those days to make a 365 year again. And so we reduce the complexity of the model by taking these 8,760 hours, and we choose typical days, and then we stitch those days together, and that allows us to get a representative year that has that chronology, but much simpler complexity in terms of the computation. So instead of having to run 8760, so hourly for the year, for many years, we can run this computationally simpler, but we still have that chronology in the system.
Okay, so
I can add more details of that individually. If you want to send me an email, that would be worth doing. Actually, I can go to my last slide, which has my email on it.
perfect.
Right at the bottom there. So there's my email. Feel free to send me an email if you have specific questions like that. I can either answer them directly. If I know the answer, I can get you in touch with the modeling team who will be able to answer in a lot more detail.
That's excellent, Taco. So, and I'm going to look here once more. There was a question about PDHs. I have to get back to folks on that. Maybe post a note on the with the seminar series information. I don't have that right now readily available. And I think so. Those were the three questions. The water to run nuclear resources is there.
Yeah, I see a question on using hydro to store power, sort of using pumped
Ah,
hydro
yes. Yeah,
with the
that was the
hydro.
last one, I think. Yeah.
Yeah. So that one, yeah. So that we currently do not have pumped hydro in the model. The model could easily be added. Pumped hydro could easily be added. There was a study a few years back on doing pumped hydro at I think it was a mica reservoir to pump from Breville Stoke back up into mica. And at that time, it was not financially feasible to do that, but it is possible to do that in the model. And yeah, the flexibility of hydro is really valuable. Depending also on the timing of when the different inflows come. And so we can add that. That's actually a relatively easy add to say, could we pump water back up?
Yeah,
To make
that
that.
that was yeah,
Yeah,
that's technology that's been used really
yeah,
early on in Europe, right?
yeah, yeah.
Yeah,
And you
very
need the
much so.
geography. We have good geography in BC.
Yeah.
Maybe in Saskatchewan, it's a little harder to do pump storage because it's a little flatter. Yeah, so.
There was another question at the very beginning about the Federal Energy Regulatory Commission. Are you working with them or like what is the collaboration with various agencies across North America?
So I do not have any work with the like FERC or NERC or any or the Western Electricity Interconnect group, WEC. I don't have any specific direct links with them. I do have links with, or I have conversations with provincial government, federal government in terms of both their modeling in Canada, the modeling that they do, as well as the sort of the policy questions that they might have. We have some discussions there, and so there's some discussion with our USA model and their Canada model. Can we get some trade happening between those two? Some pieces like that. So there's definitely conversations with different regulatory agencies. FERC and NERC are more how does the system operate regulatory versus how do we expand the system. That's more the utilities. So the BC Hydros, the Fortises, and things like that would be more on how do we build out the system to effectively meet demand. So
Yeah, so this is interesting. So do the models differ? Like if for like actually what I was getting at, like between the different models done
mhm.
by the different organizations, like is there a convergence in the
Right, yeah,
outcome
yeah, very
or not?
interesting question, and I think that's one of the strengths of having multiple modeling teams. If we get similar results that are all driving to the same direction, we have to build X. We know
Yeah,
we probably have to build X. If we get different results, that gives us an opportunity to really understand what's happening in those two different pieces. What are those different, um, why does one model choose A versus the other model choosing B? What are the different assumptions that are in those two models? And then what are the reasons for those two activities to happen? And that gives us lots of really interesting knowledge. It's actually quite boring if all the models say X, because then we're like, okay, I guess we're doing X. But if we say, well, one model says X, this other model says Y, this other model says Z, then we have an interesting discussion of what are the assumptions in each of those models, and can we do a good job of reducing the uncertainty of those assumptions so that we get knowledge out of that? So
yeah, I agree. This would be a
yeah,
terrific opportunity to grow, right?
exactly. Yeah, yeah.
So we have just gone about 4 minutes over.
Hmm.
So I'm getting the signals here.
Okay.
So maybe we can uh, give a big hand of thank you to Dr. Taco Niet. It was a terrific session. Thank you very much. And I'd also like to thank all of our organizers, all the people who have been working on this series to make this possible. So thank you very much
Mhm.
to all of those. and our participants, because we got some really good, interesting questions. And hopefully we can continue the discussion at the next talk on April 23rd with Dr. Jin Jiang from Western University in Ontario, giving us an overview of essentially the development of nuclear technology in Canada from the beginning to today's status. Okay. So thank you very much, everybody, and goodbye.
And I'm happy to answer questions via email if I didn't manage to answer them online. So,
of course, yes. So
thanks everyone for organizing. It's really fun.
Thank you very much. So reiterating the email address.
It's here, for Niet at sfu.ca, right at the bottom of the corner there.
Thank you very much. So for